A primary goal in preclinical stroke research is measuring the exact degree of sensory motor recovery following focal ischemia. To do that, researchers must quantify highly specific, subtle signs of hemiparesis. The gold standard for measuring these deficits relies on two specific behavioral assays, the grid walking test and the horizontal ladder test. The methodological bottleneck for both of these behavioral assays is human labor. Trained observers must sit and conduct subjective, time-intensive, frame-by-frame analyses to tally individual foot faults. The industry's attempted solution to this time constraint is proprietary hardware equipped with infrared beam break arrays designed to automate the step-counting process. Scaling preclinical behavioral phenotyping certainly demands high-throughput automation, but accelerating data collection has no scientific value if the hardware lacks the kinematic sensitivity required to detect the specific motor deficits it was built to measure. This experimental timeline maps our approach. On day 0, a photothrombotic stroke model induced focal unilateral motor deficits. Impairment was measured on post-stroke days 3, 7, and 14, using the grid walking test and the automated ladder test. Running the exact same cohort of mice through both assays isolates the tracking technology itself as the sole independent variable. The data allows us to test whether commercial beam break hardware accurately registers the focal physical deficit created by a confirmed cortical infarct. These Crescell violet-stained brain sections establish the biological ground truth of the experiment. Every mouse in the stroke cohort suffered distinct, histologically confirmed damage to the right hemisphere primary motor cortex. This graph tracks the manual grid walking scores for those exact subjects. By post-stroke day 3, human scores log a massive spike in missteps for the affected contralateral forepaw. The error rate triples, hitting roughly 22%. Now look at the bottom graph, charting the automated ladder test data for the exact same mice. The automated hardware registered an error rate between 5 and 8%. This is a flat line, statistically indistinguishable from the healthy sham group. An industry-standard hardware system recorded 0 functional impairment in test subjects carrying verified brain damage and visually obvious hemiparesis. The failure lies in the engineering mechanics of the commercial biosub ladder test. The system relies on 2 horizontal infrared beam lines, one above the rung and one below. During a correct placement, the paw breaks the top beam and naturally remains above the lower beam. However, post-stroke hemiparesis often presents as a slight slip. The animal's paw falters, dropping just a fraction of an inch below the top of the rung. Because the paw does not fall low enough to break the bottom infrared line, the proprietary hardware categorizes the slight slip as a successful step. Binary beam break hardware abstracts away the kinematic reality of focal unilateral deficits. A system that only reads ones and zeros consistently misclassifies subtle impairment as normal locomotion. An alternative to binary physical sensors is high-resolution software, specifically markerless pose estimation using DeepLabCut. This anatomical map shows the parameters used to train a neural network to track specific rodent locomotion. It maps 8 key joints alongside 4 specific misstep annotations. A ResNet 50 backbone was trained on over 4,000 manually annotated frames. These frames were drawn from multiple camera angles to guarantee spatial robustness. Looking at the cross-entropy loss curve, we can evaluate the model's accuracy. The curve stabilizes below a 0.002 cross-entropy loss threshold. This yields a sub-centimeter tracking error of 0.11 centimeters. A continuous 2D kinematic software overlay tracks the exact coordinate of the paw at every moment. It maintains the spatial resolution necessary to measure complex behavioral phenotypes that physical hardware ignores. This chart plots the data generated directly from the pose estimation model applied to the grid walking videos. The software correctly detects a nearly 3-fold spike in affected forepaw missteps at post-stroke day 3. When the human expert's manual scoring curve is overlaid onto the AI detection curve, their shapes match almost perfectly. Both methodologies track the exact same recovery trajectory out to post-stroke day 14. Open-source pose estimation successfully replicates the specific spatial judgment of a trained human scorer. It delivers high-resolution behavioral data while completely bypassing the manual labor bottleneck. This bland Altman plot tests statistical reliability against human observation. The data shows a mean bias of just 3 percentage points. While the software slightly underestimates total missteps, it maintains extremely tight consistency across the dataset. To evaluate discriminative performance, we look at the receiver operating characteristic curve. The model achieved an area under the curve of 0.925. This indicates a highly favorable true positive to false positive detection ratio. This rigorous validation establishes pose estimation as a mathematically sound laboratory methodology, ready for broad scientific application. This scatter plot connects validated behavioral scores directly back to physical brain damage. Just like manual human tracking, the DeepLabCut system yields behavioral data that scales linearly with histological infarct volume. Legacy bean brake systems lack the precision to measure unilateral stroke deficits. They fail to capture the nuanced kinematics required to evaluate motor recovery. Replacing proprietary physical arrays with open-source DeepLabCut pipelines provides an immediate, scalable, and highly cost-effective solution for research facilities. Machine learning-assisted video analysis offers the high-throughput volume laboratories need without sacrificing the biological accuracy they require.